Good. So this is Detock, High Performance Multi-Region Transactions at Scale. It was published last year, and I basically did not understand it. I tried fairly hard over the weekend, but I should have given myself some more time. There are parts where I know that I don't know, and then there are other parts where I think that I know, but I could be wrong. So I'm going to ask you all questions, and you should feel free to interrupt me if you understood the paper better, or think you did, and uh, and I'm saying something that you think is wrong. So the goals of this paper, they want strictly serializable transactions that is externally consistent, and they want them to be multi-region across data centers that are distributed around the world that have high latency between them. They want also low latency and high throughput under high contention. And they want to specifically make sure that they handle contention between multi and single region transactions within each of these regions. And this paper is part of a whole research lineage on deterministic DBs. The first one that I know of was Calvin, which was published in 2012. I've read it a couple of times, although it's been a while since I've read it. I only recently realized that it's named Calvin after the Protestant theologian who claimed that we are predetermined to go to heaven or hell in the same way that transactions are predetermined to execute in a certain way. More recently, there was Slog, which is applying deterministic transactions to geo-replication. And then there's Detock, and Detock is very close to Slog. It uses some of the same code, it uses the same architecture, but Detock has different conflict resolution rules from Slog. So that's going to be the main focus of this paper. The architecture of Detock, this is a diagram from the paper. It's partitioned and it's also distributed across geographic regions. A region can have multiple partitions in it, and each item in the data store has one home region. So the home region holds the authoritative fresh copy of that item. The home region is where the item is updated. And then the item can be asynchronously replicated from its home region to other regions. And the other regions are basically a read-only cache of non-local data. So as kind of an introduction, let's talk about how a single home transaction would be executed. Well, actually, any transaction. So a transaction arrives at the top of the stack at the forwarder of some arbitrary region. And that partition becomes the coordinator for this transaction. Transactions are always one shot. That's a requirement of deterministic databases. So we can't do SQL style conversational transactions. So this has been true from Calvin and forward. That means that the read and write set of the transaction is always known at the beginning. Either they're explicitly declared by the client or they're determined with static analysis of the code of the transaction if it's some sort of procedure. Or the coordinator could do a reconnaissance transaction, which is a dry run where it gathers the read and write set by executing the transaction on all relevant regions. And then there's an algorithm for checking whether that read and write set are still valid when the transaction tries to execute for real. And we're not going to talk about that. So the coordinator, somehow it knows the items that the transaction is going to read or write, and it has something called a home directory, which is a map of regions to data items. So the coordinator knows from this what regions participate in the transaction. And it annotates the read and write sets with their regions. And then it forwards this annotated transaction to all of the participant regions. If it's a single home transaction, then it's just put in one region's log. And the logs are stored in batches, and the database starts a new batch every 5 milliseconds. The paper says this, but I don't know why it matters. Why did they choose 5 milliseconds? What role do these batches play in the larger algorithm? I think they might just mean that they write the log durably to disk every 5 milliseconds, and so they're batching it up to minimize disk I/O. Somebody chime in if you think that there was more to it than that.
Yeah. Can it be like the scheduling issues, like a hierarchical scheduling? You schedule the batches, and then you schedule stuff inside the batches.
Right, that would be what Calvin does. And I was expecting to see that in this paper too, and then I didn't see it in this paper. So I'm unclear about whether they're doing that or not. Anyway, transactions are stored in the logs, and then they're asynchronously replicated between regions. And single home transactions, because they're just totally ordered in a sequence, they can be arranged according to their dependencies, and there won't be any dependency cycles. The paper explains why single home transactions can't have dependency cycles with each other. And I think basically it's just because they are one-shot transactions which all arrive in a single request. And they've already been totally ordered by the sequencer. So they don't have any cycles, therefore there are no deadlocks. So the scheduler just dispatches them to workers in a straightforward way. Whenever all of a transaction's dependencies have finished, then this transaction can run next. There can also be single home transactions, meaning that they're in one region, but they are running on multiple partitions. So there's still distributed transactions, but the Detock paper doesn't think that these are interesting. The paper just says that transactions accessing multiple partitions in the same replica follow a deterministic execution protocol similar to Calvin, and this does not require a two-phase commit. So Alexei, maybe you're right that we are using these 5 millisecond batches in the same way that Calvin does. Maybe that's the answer to multi-partition, single region transactions and how they avoid coordination. Each region's local log is being asynchronously replicated to all the other regions. So all of the regions are replicating all of the other regions' transactions at different times. So there's no coordination between them for replication. So when a region replicates a remote log, it plays those remote transactions on its copy of the remote data to update that copy. So I think that this makes all of these copies eventually consistent. And that's it. There's no stronger guarantee about all of the data in the system. So that's single region transactions. They're pretty straightforward. They're basically just sent to the region and executed. So the interesting part is going to be multi-home transactions. So once again, let's say that a transaction comes to some region and its list of items now spans multiple regions. So the forwarder has figured out from its home directory that this is a multi-region transaction. And I'm going to kind of simplify the diagram here like this. So transaction T1, it arrives at region A, and the forwarder sends it on to region B because this transaction affects both regions. the forwarders then create these things called graph placement transactions. And a graph placement transaction is the part of the transaction that only uses keys in one region. So T1A is the part of the transaction on keys in region A, same for T1B. Graph placement transactions are like single home transactions. They only affect local data. So they're just added to a batch by the sequencer, just like single home transactions. But scheduling them is going to be quite complex. So let's say that another transaction, T2, arrives at region B at around the same time. And transaction T2 is also a multi-region transaction. So it also is forwarded and it produces two graph placement transactions, T2A and T2B. And let's say that they're sequenced like this, where in region B, transaction 2 is sequenced first, and in region A, transaction 1 is sequenced first. So they're sequenced in different orders. After that, just like we saw before, they are batches, mature every 5 milliseconds. They're added to the logs, and the logs are asynchronously replicated. Here's another question. Why are we doing this replication here? Because it seems to me that the forwarder at the top of the diagram knows everything about each of these transactions. Like region A actually knows all of the region B keys that both of the transactions are going to work on. And so it could generate the graph placement transactions for all of the keys. I don't understand. It's as if region A's log manager needs information from region B and vice versa, but I don't actually see why that's the case, because we already had this this exchange at the top. By the way, are you seeing my slides advance as I talk?
Yeah.
Yes.
Okay, good. I'm using my iPad for something, and so it doesn't look correct to me. Okay, so you see a red Y at the bottom of this slide, right?
Yeah.
Yes.
Okay, good. Okay.
Do we need this like Y because of the order that the log manager imposes on those?
Oh, maybe that's an interesting idea. Maybe that's what it's learning. Huh. Okay, let's keep that in mind. That might be the answer.
It needs like deterministic stuff, right? So this order may be like that seed of determinism.
Right.
They're sequenced separately. So T2B, T1B are sequenced after region A learns about the transaction. So I bet it needs to exchange ordering information there.
Cool. Okay, that sounds very plausible. Let's keep that in mind. After this, they are sent onto the scheduler. In different regions, they're going to arrive at the scheduler in different orders. So maybe in region A, transaction A arrives before B, or vice versa. The scheduler can't just execute transactions as soon as possible once all of the conflicting transactions are finished, because that would lead to different outcomes in different regions. So we need some deterministic way for all of these graph placement transactions to be executed in the same order everywhere, even though they're asynchronously replicated. So my understanding is that this is the part where Detock really diverges substantially from slog. And I have a lot of questions about this too. So the paper says graph placement transactions establish an order between multi-home and single-home transactions at the region that generated the graph placement transaction. However, they do not globally order multi-home transactions, since different regions may generate graph placement transactions for a set of multi-home transactions in different orders. Thus, there is a concern that the generated graph may contain cycles which would lead to deadlock during processing. So they start this off with a simplified example, and then they talk about the whole thing. So the simplified example is, imagine that you know all the transactions that are ever going to occur, and you know the dependencies among them. You can condense the dependency graph into strongly connected components. So we're talking about a hypothetical where there's just one finite set of transactions that are all known in advance. And they talk about this algorithm called condensation. Condensation is identifying strongly connected components. And a strongly connected component is a subgraph where every node is reachable from every other. So you can see in any one of those circled orange subgraphs, starting from any node, you can reach any other node in there. But for the graph as a whole, that's not true. You could start at one node and it's not reachable from another node. So we identify these SCCs, and by definition, the dependencies among the SCCs do not have a cycle because you've isolated all of the cycles into an SCC. So you can resolve deadlocks within an SCC by just running the transactions by sorting them by their unique IDs. The transactions were assigned unique IDs by their coordinators. And then, although there's no parallelism, but you do resolve the deadlocks. And then among the SCCs, the scheduling is just a topological sort where you execute a subgraph as soon as all of its dependencies are finished. Whew. So that's the algorithm, which I think I understand, for if we knew all of the transactions up front.
Just, I guess, a quick note. This is pretty much the algorithm of the heap access.
It's the algorithm of what, Alex?
Heap access.
Oh, really? Uh-huh.
So it's kind of, the gist of it is the same, right? So in heap access, you construct the graph, you isolate from the connected components, and then you order SCCs and then deterministically order stuff within the SCC.
Gotcha. Okay, one sec. Let me do some more AV. Okay. Can you see my screen once again?
Yeah, good.
Yes. Okay, good. So here's the algorithm for figuring out when a transaction is ready to be scheduled. They say that for every vertex corresponding to a multi-home transaction T in the dependency graph, let GP total be the total number of graph placement transactions generated for T. So GP total is basically just the number of regions that the transaction affects, because that's the number of graph placement transactions. And we can know this from the forwarder can already calculate this number. So a counter GP is associated with T to keep track of the number of graph placement transactions of T that have been added to the graph so far. So this is when the scheduler in one region is deciding when a transaction is ready to go. It's waiting for all of those graph placement transactions from all of the regions to be asynchronously replicated back to this region so that it knows that it has all of the information it needs for T. So a complete vertex, it's either a single home transaction or it's a multi-home transaction with GP equal to GP total. So that means that we've replicated all of the graph placement transactions for T. And a stable vertex T is both complete and also there's no path going from an incomplete vertex to T. So it means that we have all of the graph placement transactions for T and the same for all of the transactions it depends on. The claim then, I think, is that a stable subgraph is made of all stable vertexes and you can schedule it and execute it at your region with no coordination with the other regions. And all of the regions will execute the same transactions in the same order. And the example they show here is that on the left, that Y is incomplete because X hasn't arrived at this scheduler yet. But on the right, once X does arrive, then Y is complete. And in fact, its whole subgraph is now complete and ready to go. And this I didn't understand because how does the scheduler know that X is going to arrive? Basically, what if all the graph placement transactions for Y arrive at this region before any for X have? So this scheduler doesn't know that X exists at all, whereas some other scheduler does know that X, and so waits for X to be complete before it schedules all these transactions, whereas the previous region doesn't. I don't understand how we avoid coordination to make sure that all the regions know about enough transactions to schedule them in the same order. Especially because we're trying to guarantee strict serializability. I don't get how this algorithm achieves that. And that is as far as I got with this paper. There's other stuff like home changing transactions that move items from one home to another, which I might tackle in the future, but for the moment, since I didn't even understand this much, I decided not to deal with that. And I also didn't read the evaluation yet.